Hey, what's up, RT230s? This is Mr. Tagazon here on the Mr. Tagazon channel on YouTube. And we're going to be talking about Chapter 6 in Pilbeams, which I have termed Set Me Up So I Can Flow. Okay? From the greatest 80s band in the world, Wham. Just kidding. But it's from Wham. Wake Me Up Before I Go. Alright? That's just the title. Let's delve right into it. Alright, so when we're determining initial event settings, we want to consider metabolic rate and caloric intake. Now, with metabolic rate, as you start to fight infection, your body starts to need more energy. Okay, so it increases metabolism. So therefore, it's going to increase your minute ventilation because you're producing a lot more energy and you're using up a lot more energy. Therefore, you're using up a lot of oxygen and you're going to create a lot more carbon dioxide. So you're going to have to blow off more carbon dioxide as you increase your metabolism. Okay, and so then we also look at our body surface area. So when we estimate body surface area, for men it's 4 times our body surface area, and for women it's 3.5 times body surface area. Are you going to be tested on this? No. Is it going to be on the NBRC? No. Is it in Pilbeams Chapter 6? Yes. So that's why I'm just briefly going over it. Alright, so we can increase our minute ventilation because of the increase in temperature. So again, like I said, if I was fighting infection or if I was exercising, I am burning up more fuel in the form of carbs first and then fats. So I'm burning up a lot more and I'm using more energy, so therefore I'm going to be using up more oxygen and I'm going to be blowing out more carbon dioxide. So I'm going to have to increase my minute ventilation so I can blow off all that CO2. Okay, so that's where when you're exercising you increase your respiratory rate and most likely you shorten your tidal volume. Okay, so if you ran a mile and you're done, you're just huffing and puffing, right? So that means you have low volumes, but it's going to compensate. High respiratory rate, all right? Because you're blowing off that extra CO2 that you just created. Okay, so you can decrease your minute ventilation, and it's down here it says 9% Celsius between 35 and 37. 37 Celsius is our normal body temperature. That equates to 98.6 in Fahrenheit, I believe. Please in the comment section let me know if that's right or wrong. But when we talk about decreasing minute ventilation, so if we drop down for 36 or 35, we're going to decrease our minute ventilation by roughly around 9%. I don't like working with percentages, unfortunately, so I don't think you guys like it either. So in the homework, do your best to try to calculate all these. Worst case scenario, if you don't feel like you understand this, it's okay. I won't mark you off for it. Okay, so let's talk about the nitty-gritty here. This is one of the main concepts you will need to know for the exam and for the rest of your respiratory career. It's your ideal body weight. Most of the time the doctors will just give you vent settings, but if you're able to calculate ideal body weight, you're going to be able to give the patient or meet the patient's oxygen and ventilation demands based on their ideal body weight. So like I said in lab, this is the old school way of calculating it. You have Egan's and you have Kettering. I'm not sure if Dana Oaks reflects this, but the reason why I'm using this old school way is because the homework answers and the test answers will be correct if you use this way of calculating ideal body weight. Okay, so again, in red is the formulas for men and for women. Just remember that it comes out into pounds, and you have to divide that answer by 2.2 to convert to kilograms. Okay, so, and then also to just want to reiterate that there are mechanical dead space considerations. Mechanical dead space meaning the extra tubing that we have, our circuits. If you have an Omniflex, if you also add some extra tubing, if you let's say from the Y, you connect the HME, okay, right? So from the Y you connect HME, and then you connect the T piece for your nebulizer, and then you put in 1 or 2 links of corrugated tubing, and then you connect it to the ballard. Hopefully you guys could visualize that. So if you put, let's say, 2, 3, 4 links, or four times as much corrugated tubing, that's adding more mechanical dead space. And the more mechanical dead space you add, the increase the chances of your flow being turbulent. Okay, so when you have turbulent flow, the oxygen is not getting into the lungs, and therefore you're not hitting the volumes that you should be getting. So with minute ventilation, we have our equation. It's respiratory rate times tidal volume. You're going to become very familiar with that. Okay, and so for the second and third equations, I have algebraically solved for the tidal volume and respiratory rate. So if I gave you different values, for example, if I gave you the minute ventilation and the respiratory rate, you should be able to calculate the tidal volume. And again, also too, with the respiratory rate, if I give you the minute ventilation and tidal volume, you can solve for the respiratory rate. Okay? All right, and so at the bottom here, it says minute ventilation is about 100 mLs per kilogram of ideal body weight. Now, if let's just say I gave you a weight in kilograms and that's it. That's all you know. Then go ahead and utilize this, I guess you can say just this concept, because it's a good estimate. Okay, so you know, if I give you like someone who has 72 kilograms ideal body weight, right? I don't let you calculate. I don't give you a height. I just give you that, and I ask you what would be the minute ventilation. So a 75 kilo person, it would be 7.5 liters. Okay, so that would be a really good estimate and a faster way, but don't think that you can just always use this way. If I give you a height on the exam, just use that and calculate ideal body weight. That would give you the best answer. So here, box 6.5 in your text, this tells you the relationship between total cycle time, flow rate, and all that jazz. So I want you to look at total cycle time. That just basically means the time it takes to breathe in and the time it takes to breathe out. That whole thing is one cycle. Okay, so just to take it back to when I talk about certain mechanical ventilation modes, and you're talking about time cycled, this is what it's talking about. It's dealing about the total cycle time, how long it takes for one inspiration and one expiration. Okay, so again, this kind of breaks down just the different relationships. Okay, so you have the concept of total cycle time. You have the concept of an IE ratio. Okay, and then you also have, well, actually, let me take a step back. Let's go down here. So with the IE ratio, your I time always has to be 1, unless you're doing an inverse ratio, which I don't have you do in the class. Okay, so you don't have to worry about inverse ratios. You might have a question on the homework. So just remember, if it's an inverse ratio, that means you're going to have a longer I time and a shorter E time. Okay, it's inverse, right? So it's not 1:2, 1:3. It'll say 2:1, 3:1. That would be considered an inverse ratio. But when you talk about IE ratios and you're solving for it, you have to have the I time at 1. Okay, so then when you divide the E time into the number that you've divided into your I time, then that's going to give you a certain amount. It might give you 3.2, 3.7, 2.8. So it's going to give you a decimal. Okay, just for sure. So, well, I think I have something like a way to solve for that later on in the slides, hopefully. All right, so I don't want to confuse you even more. All right, so then, yeah, this is just showing you just the relationships between expiratory time, total cycle time, respiratory rate. You have that in box 6.5. So this is the love triangle here. You have your I time equals tidal volume divided by the flow. So all of these three have a triangular relationship, and you can solve for each algebraically. Okay, so when we're talking about flow, you are going to convert to liters per second. Okay, so if I give you a flow rate of 40 liters per minute or 60 liters per minute, you got to convert that to seconds before you do any other calculation. So here's an example here. I have a tidal volume of 500, I time of 1 second, and we need to find the flow. Okay, so algebraically, I have determined that x is your flow, so it's tidal volume divided by I time. So, which is great because your I time is 1 second, so 500 divided by 1 is 500 mLs or 0.5 liters per second. Okay, so therefore our flow, let me take a look, it's liters per second. So if I wanted it, flow is usually liters per minute. When we talk about mechanical ventilation, it's liters per minute, but when we talk about equations, it's liters per second. So that's why I converted it back to liters per minute in this example. All right, so we have the concept of total cycle time, TCT, as I usually like to call it. Again, total cycle time is your I time plus your E time. Easy peasy lemon squeezy, right? So if I gave you this example, 25 breaths per minute, all right, divided by 60 seconds, so it's 2.4, this should say seconds per breath. Okay, I apologize for the slide. It should be 2.4 seconds per breath. So my total cycle time is 2.4 seconds. All right, so that means when I breathe in and when I breathe out, that equates to 2.4. So then if my I time is going to be 0.75 seconds, what is my E time? So what I'm going to do here is I'm going to take my total cycle time, which is 2.4, minus my I time, which is 0.75. That gives me an E time of 1.65 seconds. Now again, so the example is that, right, 25 breaths per minute gives me a 2.4 seconds per breath. Okay, so again, I can give you the I time, I can give you the E time. You would have to calculate the other. But here I'm showing you that you can algebraically solve for either E time, I time, or just utilize the formula for your total cycle time. So when we talk about initial vent settings per Pilbeams, okay, and you guys have that cheat sheet that I gave you in lab where it has all the normal values. So our tidal volume is 6 to 8 mLs per kilogram body weight. That's what we will use. So once I get my ideal body weight, convert to kilograms, I'm going to multiply that number by 6 and by 8. That's going to give me my range. Okay, so, and here's the thing though, I mean, if you are like me, if you like to split the uprights and you want to go with 7, then go right ahead. But put it this way, if you get a number like 420, for example, mLs, 420, it doesn't, you can't put 420 in the machine. Okay, it's only in increments of 50. So if you're at 420, I probably would round down to 400. You can't go wrong with that. And then just calculate my respiratory rate to give me my tidal volume or my minute ventilation. All right, so respiratory rate, we go 12 to 20. And in our minute ventilation, we'll go 5 to 7 liters per minute. Okay, so you want to make sure that your minute ventilation falls under that range. And once you have that, then you're set with the, I would probably say you're set with the parameters that deal with your PaCO2. Okay, so once that's done, then you turn your attention to oxygenation, which is your FiO2 and your PEEP. Per Pilbeams, they want you to start off between 40 to 60. Okay, and also with your PEEP, you can start at +3, or you can start at +4 or +5. So either one of those is good. A lot of times the doctors put the +5 because we have an anatomic PEEP of +5, so they just want to mimic what our body naturally has. Okay, so when we talk about inspiratory flow, okay, and flow patterns. All right, so flow patterns is going to be dealt more with chapter 6 in graphics. So but I'm going to briefly touch on a couple ones. But for the meantime, we're looking at rate of gas flow. Okay, so I want you to look at these two concepts here. Shorter I times result in higher peak pressures. Okay, so when you have a shorter I time, your peak pressures will rise. Why? Because I need to generate so much flow to get the lungs increase. So along with some flow, I'm gonna have to generate some pressure. All right, pressure is gonna exert against the walls of the lungs, and it's gonna inflate them. It's gonna exert some pressure in the walls of the alveoli, so I can inflate them. And if I have any type of atelectasis, there's going to be a lot of pressure exerting against the walls of the alveoli. So that's where that concept comes in. Now, the one in red, it says slower flows may reduce peak pressures. That's great, but actually, let me read it real quick. Slower flows may reduce peak pressures, improve gas distribution, shorten expiratory time, and increase mean air rate pressures. Okay, so slower flows could do all of that, which is great, but again, with our COPDers, this would be the exception. You don't want a slower flow. You want a faster flow rate so you can shorten your I time, so you can give them a longer E time for them to breathe out the extra CO2, and you also prevent them from air trapping, right? Okay, so when we talk about flow patterns, we're talking about two different ones. As for right now, you have the constant flow or the square waveform or square flow pattern, and the descending. Okay, so the descending is what you will see when you have high flows. So a descending pattern, it just goes straight up and then it will just start to angle downward, versus your constant flow it's just a square. It goes up, it stays the same, and then it goes back down. So a constant flow is when something's being controlled. Okay, so let's just say if you were on pressure control and you looked at your pressure scalar graph and you see that it goes up and then it might plateau and then it go back down, that just means you're in pressure control. And vice versa with volumes. But there are times where on the ventilator graphs, it just shows more of a pointed type of top rather than it being flat. Okay, but just let you know that constant means it's a square form and that it is being controlled. So here's a couple of flow patterns that we will normally see, or we're going to see in graphics chapter 9. But again, here's your rectangular or your constant, and then here's your descending ramp. So this would be more of your faster flow, because you need the flow there fast and then a longer expiratory time. So descending ramp would be what you would see. So those two is what we'll deal with this chapter for now, and then these other ones will go later on. So then when we're talking about flow patterns, and we're setting minute ventilation, so you might have different flow patterns, as you can see here. So I have a square flow pattern, and you'll notice that if I have it at 1 liter a second, it's going to stay there at 1 liter per second. Okay, versus if I have a descending, well, guess what? When I have a descending, as time goes on, my flow starts to decrease, and it decreases gradually. Now, this is good to have in terms of alveolar recruitment, because you shoot all this air in, you increase all that pressure, it's going to open up all your alveoli, and as the flow starts to descend, right, it's still maintaining that pressure. So the alveoli are going to be open much longer on a descending ramp versus if I had a constant. So if I had a constant or a square waveform, once it hits, I'm going to safely assume that's 1 second, it's just going to drop. That's it. So within 1 second, it's going to be at its max, versus on the flow, when it hits, let's say 1.5, you still have pressure in the alveoli. And then if you're hitting close to 2, there's still going to be some pressure there. So that's going to help oxygenate your patient. So a descending flow pattern is really, really good. Okay, so when we look at the bottom graph here, we're looking at volume over time. So this is a volume scalar. Okay, so if I have, in terms of volume, if I have a short time to, this is more of a ascending. Okay, so as I as I shoot flow, so my volume is going to start to rise, and then right when it hits that peak, my flow stops, and that's when my volumes drop. But again, if I have a descending flow pattern, it's going to create a longer time for my volume. Okay, so as I shoot high up, I start at 1 liter per second, I start losing it. So here it's just going to gradually increase. Okay, this is great except for when you have a COPD patient. Okay, so all this time the volume's ramping up, and right when my flow's done, that's when it reaches it. So just remember, with the descending flow pattern, that's great to keep a lot of pressure open, but in the same sense, it's going to take a long time for the lungs to fill. Okay, versus our constant flow pattern, right, and it hits right when it ends, the flow ends and it kicks back in again, I'm going to be starting at 1 liter a second. Okay, so then if I stay with that, I'm gonna get to my volume at a faster time. Okay, hopefully that that doesn't confuse you. Okay, so with the waveforms, the main things here. Okay, so the mean airway pressure is higher with descending flow waveforms. We've talked about that because as it starts to descend, I still have pressure within the alveoli. So that's why my mean airway pressure is higher, because there's a lot more pressure over time. Okay, so peak inspiratory pressure is higher with ascending flow waveforms and lower with descending waveforms. So as your PIP gets higher, so again, the ascending waveform, we're looking at that in the volume part of the graph in the last slide. So your peak inspiratory starts going higher with an ascending wave flow, because the flow starts ramping up. So that's going to drive your peak pressures higher. Okay. So when you have a descending flow waveform, okay, it's still going to increase your peak inspiratory pressure. Okay. So just be mindful of that, because if you have someone with ICP, or you're looking at someone whose static compliance starts to increase, then you might have to consider a different type of waveform. Okay. So descending waveforms improve gas distribution. That's actually that is correct, because remember, descending waveforms, you still have pressures going off, and the pressure doesn't just stop cold turkey. It starts to ramp down, so therefore it's going to keep the alveoli much more open, and so that's why you're going to improve your gas distribution. Okay, and last but not least, descending waveforms are created during pressure-targeted ventilation and can improve arterial oxygenation. And again, descending waveforms, you're constantly having pressure instead of just stopping cold turkey. You're ramping down from from the height of that flow. Okay, so therefore, when you have flow and then you have your pressure, then it starts ramping downwards. So that also helps oxygenation and ventilation as well, because again, you're keeping those alveoli open. You can get more gas exchange that way. All right, so when we're talking about an inspiratory pause, we all know this, right? We should know all this already. Inspiratory pause gives you the plateau pressure. Okay, let's see. So plateau, improved distribution of air throughout the lungs, not in patients with COPD and flow limitations. So this is going to be with COPDers, it's going to be a little bit more difficult to generate that plateau pressure because they have that air trapping. So you may not get a correct plateau pressure. And then it says pause not commonly used in clinical practice. We really don't calculate, or we don't get plateau pressures. There are certain hospitals, like when I used to work for, oh gosh, I'm blanking out. It was in LA. Well, anyway, we did have to calculate plateau pressures. We had an Esprit. I couldn't remember how to do plateau pressures on Esprit, but with the PB840, I mean, you guys already know how easy it is to do that. So plateau pressures, again, that's with the inspiratory pause. All right, so when we're talking about vent settings during pressure ventilation, all right, so again, setting baseline pressures or PEEP. Okay, so again, baseline pressure is the same as PEEP. I want you guys to understand that. Determining tidal volume and pressure ventilation. So what we're doing here is measure plateau and baseline pressure after initial volume targeted breath. All right, so when we're looking at our tidal volume and pressure, Okay, so to manipulate our tidal volume in pressure ventilation or pressure control, we have to first and foremost get our plateau pressure while we're on volume control. Once we get that plateau pressure number, we switch to pressure control and we plug in that plateau number. Okay, that is our baseline pressure. Okay, and then after that, you look at, based on that pressure, what volume is it getting. So for example, if I had a plateau pressure of 21, I convert to pressure control. I'm going to start my pressure at 21. Okay, so therefore after that I'm going to look at what volume am I getting at a pressure of 21. If I'm getting pretty high volumes, let's say I'm getting 550, and originally in volume control I had a order of 500, I might drop down the pressure a bit so that I can get it to at least 500. Okay, so again, we manipulate the pressure to get the volumes that we want. Okay, so again, it says check tidal volume and adjust after initiating pressure ventilation at low pressure. So let's just say hypothetically, your plateau pressures are in the 40s. They're above 30. Okay, for pressure control, our magic number is 30. If any number goes above 30, right, we have to start considering switching to pressure control. So if on volume control, my plateau pressure is at 40, I can't use that as a starting baseline for pressure control. So what I would have to do is I would have to start off at a range of 10 to 15 centimeters of water pressure first. Okay, then I would titrate up based on the volume that my patient is breathing. Okay. And then we also have initial vent settings for our pressure support, pressure control, and our BiPAP, which we'll talk about. Okay, so initial vent settings for pressure control. This is what I said before. You have to get your plateau pressure first on volume control, and then you switch them over. Okay, then that plateau pressure becomes your initial pressure on pressure control. So again, if you cannot get a plateau pressure for some strange reason, then it says here you can use the peak pressure from volume control -5. Okay, so PIP -5 you can use as well. Okay, so if that's if your peak pressures are not really high. So if I'm getting a plateau pressure of 32, guess what? My peak pressure is going to be a lot higher. So that formula won't work. Okay, but if my plateau pressure is roughly around 30, this might work. I can just start my pressure control at 25. Okay. Again, here it says if the volume readings are unavailable, then we can set our pressure to 10 to 15. So that'd be our starting. And again, we want to keep the PIP less than 30. Okay, because we don't want to overinflate our alveoli. Pardon me. So again, when we talk about looking at pressure support ventilation, all right, so pressure support is basically PIP minus plateau. So it's the beginning part of our airway resistance. So think of pressure support as PIP minus plateau, but no flow, okay? Versus our airway resistance, which is PIP minus plateau divided by the flow, okay? So when we're looking at pressure support, this is how we normally adjust for it. Okay, so for pressure support, we want to increase the tidal volume up to 4 to 8 mLs per kilogram. Okay, so now remember, pressure support is you're supplementing pressure to increase the patient's spontaneous volume. Okay, so if my patient's spontaneous volume is 200, I'm going to give him some pressure support to elevate that volume to a more desirable volume, which for a patient might be 500. Okay, so hopefully I can titrate that pressure support to give them that tidal volume that would help them breathe much easier. Okay, so again, it says to decrease respiratory rate to less than 30 breaths per minute. So again, with pressure support, we don't want the patients to start going into some type of compensatory mechanism where they have increased respiratory rate because they're not getting enough volume, so therefore they're not getting enough oxygen to the brain and the rest of the body. All right, so And we want to give them that pressure support so they're getting that big volume. They're getting alveolar recruitment if needs be. They're getting oxygen and they're able to blow out their CO2. And last but not least, we don't want them to work hard. We don't want them to have an increased working rate, but we want to decrease it. Okay, and that's how we can help with that through giving some pressure support. All right, so now with BiPAP, really quickly, some of you guys have already worked with BiPAPs in your facilities and clinicals, and I know the afternoon lab I gave a quick little lecture on BiPAP. So here, this is more of the event settings. All right, so let me just point to you here in the red: patient or time triggered and flow cycled. If you see these, if there's a question that says what setting is patient or time triggered and flow cycled, please put down BiPAP, okay? Or it can say like true or false, BiPAP has a patient or time triggered and flow cycled. Yes, that's true. Okay? So our IPAP, if anything, we're going to start off at between 5 and 10 centimeters of water pressure. Okay, so we start off between there, and then from there we go with increments 3 to 5. Okay, so it says here rate of 25 breaths per minute or lower is achieved. That's what we want. We want them to either breathe spontaneously or be able to breathe at a rate that is easier for them. Okay, because remember, this is ventilation, but they are at times triggering the breath. Right, and we have our time triggered. We have our backup rate. It's time triggered if they are getting tired. Okay, and then also too, our tidal volume is 4 to 8 mLs per kilogram or more. So we want to maintain that tidal volume based on our pressures. Okay, so this is where your understanding of pressure support comes in. I'm sorry, pressure control comes in, because you're still going to utilize changing the pressures to get that tidal volume to between 4 to 8 mLs per kilogram. Okay, and last but not least, your EPAP, the second half. All right, that you're going to start at 2 to 5 centimeters of water pressure, and increase the increments from 3 to 5. Most likely, we increase the increments by 5. All right, because it's much easier. Now, here's the thing: IPAP is the same as your peak inspiratory pressure. Okay, and then your EPAP is the same as your PEEP on invasive mechanical ventilation. Okay, so when you set an EPAP of 5, that means when they breathe out, EPAP meaning let me see if I'm saying that right. End positive airway pressure, and then your IPAP is your inspiratory positive airway pressure, if I remember that right. Remember, this is it's like almost 1 in the morning. All right, this is how much I care for you guys. So hopefully that's all right. So anyway, you have your IPAP and EPAP. So your IPAP again is like your PIP, and your EPAP is like your PEEP. Okay, and the difference in between those is considered your pressure support, and therefore your pressure support helps build up your tidal volume. Okay, hopefully that helps you out. All right, so if I have BiPAP, again, we like BiPAP with our COPDers and air trapping. So with our BiPAP, you want to start off 3 to 10 centimeters of water pressure. Okay, that's for the EPAP. All right, most likely doctors might just put a 5, because it kind of somewhat splits the middle, right? So, I mean, it's increments of 5. All right, so they'll probably start it off at 5, which falls under this range. So if you have hypoxemic respiratory failure, all right, so if it's an oxygenation issue here, then I'm going to want my EPAP greater than 5 centimeters of water pressure, because I'm going to want to try to pry open or do more alveolar recruitment. Okay, so again, here it says if no improvement after about 2 hours of treatment, this mode of ventilation is probably not benefiting the patient. So again, you're monitoring the patient. Once you put them on BiPAP, and you're trying to see if they're blowing out all the CO2, if they're feeling much more comfortable, they're feeling better. But if not, then BiPAP is not the way to go. We might have to look at intubating and mechanically ventilating. Okay, So if I'm going with PRVC, now again, we're not really touching up on PRVC. It has its own chapter later on, and PRVC is a little bit different than all the other modes. It's one of the different ones. You have your APRV, you have your VAPs, you have your PRVC. Those are a little bit more advanced. They take multiple ventilator concepts into one. But for purposes of possibly homework, I threw this in here. So it says initial settings for PRVC. What we're looking at here, it says benefits of pressure breaths along with targeting a set volume. So you have both a pressure component and you have a volume component with it. Pressure release, volume control. All right, pressure limited time cycled mode that uses a set tidal volume as a feedback control. All right, so I'm going to go over this later on, but I'm just going to kind of briefly skip through this because, again, number one, it's a little bit more advanced. I want you guys to understand the basic concepts, and number two, it's not on the exam. Okay, I'm not so much of this exam. I don't know if they'll test on the NBRC. I don't think, if I recall, I don't think I've had a PRVC question on it. And so that's why we really don't heavily emphasize on PRVC, but I do go over it because you might utilize it in your clinical site. Okay, and that's basically it for chapter 6. So I hope you guys enjoyed this presentation, lecture, maybe background noise. You can wake up now. All right, guys, thank you so much, and I'll catch you in the next one.